This conference will now be recorded.
Very good morning, students. Today we'll be discussing LCR series circuit, and that too in AC alternating current. When an alternating voltage is passed through a series combination of L, C and R, then what will be the current voltage relationship? What will be the current voltage relationship? So that is actually our aim today. Okay, so what is our aim today to discuss in this session? When an AC voltage, suppose V is equal to V0 sine omega t, is passed through a series combination of inductor coil having inductance L and a capacitor having capacitance C and a resistor having resistance R. Then what is the current voltage relationship? That means what is the magnitude of the current in the circuit? Excuse me. What is the magnitude of the current in the circuit? Okay, first question which we are going to address. Second question which we are going to address is, what is the phase difference between the current in the circuit and the voltage of the source or the resultant voltage across resultant voltage across all the component. Across all the components. Okay, so these are two questions mainly we are going to address. So what is the phase difference between voltage and current in the circuit, and what is the magnitude of the current in this circuit? Okay, so look what we know. We know from Kirchhoff's law, if suppose the voltage drop across the inductor coil is VL and the voltage drop across the capacitor is VC and voltage drop across the resistor is VR, then sum of all these three will be equal to the source voltage. Okay, so which is V0 sine omega t. So this we can write readily from the circuit itself using Kirchhoff's law. Okay, I think I'll just remove the, okay, or I can just take this as vector. vector. Okay. All right. See, there are two methods of solving this circuit, or to analyze this circuit and address these questions. There are two ways, two methods. Okay. One is phasor diagram method, another one is analytical method. As I told yesterday, that analytical method is little bit complicated or elaborate, but phasor diagram method is very easy to understand and analysis and do the analysis of such circuits, AC circuits, okay, with different components. Now let me first analyze this AC circuit, AC LCR series circuit in phasor diagram method, and then we'll take up analytical and elaborate method where we have to do a lot of calculations. We'll do that also. And if time permits, then we'll discuss about the power, which is okay, power in AC circuit, or we can say power dissipated in AC circuit per cycle. We'll see that. Okay, so let me just erase this thing a little bit, or we'll go to next page. Okay, so phasor diagram method. See, what are the components we have here? We have L, C, and R. If you remember, we have already discussed all these three with sending AC signal. Suppose this is L, this is C. Separately, if we or individually, when we send AC signal, the same signal V0 sine omega t, here also V is equal to V0 sine omega t. We know what are the currents, and sorry, theta, not theta, omega t. We know, at least we know how and when you have a pure resistor circuit. So these are pure circuits, like pure C, pure capacitor circuit, pure inductor circuit, and pure resistor circuit. So in all three cases we have already seen what are the magnitude of the current. Okay, and see, I'll just write for your convenience if you have forgotten. When we have only inductor, when we have only capacitor, and when we have only resistor. See, in case of resistor circuit, see, the current will be I is equal to I0 sine omega t, same thing. There is no phase difference, right? And I0 here is V0 by R. Okay, so in this case, what was that? In this case, it was, so current will be lagging by some angle. What is that angle? By pi by 2. Okay, current will be lagging in, sorry, in case of capacitor, current will be leading by pi by 2. So it was, in case of purely capacitive circuit, this is sine omega t plus pi by 2. Okay, and see, the magnitude of this current was written as V0 by omega into, sorry, this is C, right? So 1 over omega C, that is XC, if you remember, that was XC. Okay, capacitive, I'm sorry. So capacitive reactance XC, so where XC is 1 over omega into C. And in this case, the current was I is equal to I0 sine omega t minus pi by 2. Okay, and what was the magnitude of the current? Magnitude of the current is V0 divided by XL, where XL is omega into L. So these are few informations we have already got. Okay. So when we have these informations, we know what is the phase relationship between voltage and current. See, voltage is actually leading by 90° in case of inductor. In case of pure capacitor, current is leading the voltage by 90° or pi by 2 radians. But in case of resistor, there is no phase difference. So current and voltage, they are actually going in phase. So when we draw the phasors, current phasor and voltage phasors, like say voltage drop across inductor is VL, voltage drop across capacitor is VC, and voltage drop across the resistor is VR. So if I draw all of them, see, let us suppose the current is in the, okay, no, let us suppose the current is, okay, let me just draw the this. Okay, let us suppose the current is in the y direction. Okay, current is in the y direction. So this current is this way. Okay. In case of inductor, we know the current is lagging. That means the VL will be somewhere here. VL will be somewhere here, right? By, see, it is leading by 90°, so this is I, right? And see VR and VR and the current, like the current and voltage in the purely resistive circuit, there is no phase difference. So current is this, voltage will be in the same direction. Okay, so let me add this as VR, and up to here current will be little less than V, right? Okay, so this is VR, sorry, I. So current and voltage in the resistive circuit are in the same direction, purely resistive circuit in the same direction. And see, in case of capacitor, what is the current doing? Current is actually leading the voltage by some amount. Okay, so let us say, what is that amount? Pi by 2. So let us say this is VC, this is VC. So see, this is current, this is voltage. Current, sorry, this voltage is in or across, voltage across capacitor. So there is a pi by 2 phase difference here. See, this is the current and this is the VL. So they also have the pi by 2 phase differences. So this is how we can actually draw the phasor diagram for all three components when these are separately connected to an AC source. Now suppose all three components are connected in series. In that case, how to solve this? Okay, how to solve this? Using rotating vector or phasor diagram method. See, I have VL here this way and VC this way. So I can just think that VC has got some greater value than VL, and at the same time this is negative and this is positive. So what I can do, I can take the resultant of this. Okay, the resultant of that, VC minus VL. Okay, VC minus VL, I can take this as vector as well. So VC minus VL. Okay, so this is VC minus VL and this is VR. So what will be the resultant now? Resultant voltage then? Resultant voltage will go somewhere like this, somehow like this. So which will be V. Let us say that is the resultant, and which is making an angle phi, making an angle phi with the current or VR. Okay, I'll just show you here. Let me just erase everything then. So this is, suppose, VC minus VL. I'm just taking the magnitude of them. VC minus VL, or we can take the vector notation also, nothing matters. And see, this I can draw parallelly here also for calculation. And this is VR. Say this is VR. So what will be the resultant? This one is V, say. And let us suppose this V is making an angle phi with this VR. VR means this direction is for the current also. That means the resultant voltage is making an angle phi. So what we can write from here? See, I can write VR plus VC minus VL. This resultant of this will be equal to the vector, resultant vector, right? So if I take the magnitude, let us suppose the magnitude for this is V0R. Okay, magnitude is V0R. VC minus VL magnitude. Let us say these are V0C minus V0L, kind of this. Okay. Actually, all right. Let us take in another way. Notations are not very handy here. So R 0R 0R VC magnitude VC0 VL has got magnitude like this we are taking. Okay. So sum of this must be equal to applied. This is actually applied EMF or applied voltage. Okay, this must be equal to applied voltage, right? So see, from here, if I take the magnitude of all this, then how I can write, I can write. So in this also, this has got magnitude. This has got magnitude V0 alone. Okay. So I can write from here V0 square is equal to, since this is vector sum, and they have angle, see, 90 degree. They have 90 degree angle. So I can just take VR0 square plus V0 LC VC insert square doesn't matter anyway. Square. Okay, so sorry, I'm just writing. Okay, so this could be written as well as this is suffix and prefix actually. So sorry, subscripts and superscripts only. This could be written as well. This inside the square doesn't matter, right? Inside the square doesn't matter. This doesn't matter. Okay, so this is the thing. Now see, this I know. This means I0 into R. This means I0 into XC, and this means I0 into XL. Okay, so if I put those things, look, I will get V0 square is equal to, see from here, or maybe let us write this one more line here. So this will be I0 R whole square plus I0 XL minus I0 XC whole square. So we can take I0 square common, then I get R square plus C XL minus XC whole square, right? So see what we get. So V0 square, I'll write once again what we have got. So from here, what I can get? I can get I0 square is equal to V0 square divided by R square plus XL minus XC whole square. And see from here again we can get, let me write here I0 is equal to V0 square, V0, that is the amplitude of the applied voltage, and square root of this. Okay, so this particular term is then acting as an effective resistance, right? So this is actually has given a name in AC circuit. This is acting as resistance, but this has given in AC circuit. Resistance is not called resistance in AC circuit. That is called impedance, and that is denoted by Z. We had already discussed yesterday. So this is actually impedance. Actually, modulus of impedance, or you can directly write impedance. XL minus XC whole square. See, XL minus XC and XC minus XL whole square is there, so it doesn't matter whether you write XC first and then XL, and XL first and then XC, whatever it is. Okay, so this is actually effective circuit in the effective resistance in the in LCR circuit, and this has got a name called impedance and denoted by Z, and it has got unit ohm only. Okay, ohm, since it has dimension of resistance. Okay, see, then we'll just do a little bit of things here. See what we have got. Let us just go here. Okay, I think I need to remove some of the things, otherwise it will be difficult. Let me just skip 2 lines. So this, and after that I'll directly write this one. Okay, what we have got, V0 is equal to, okay, let me write it here. So what we had got, V0 is equal to, or we had already calculated the I0. I0 is equal to V0 divided by square root of R square plus XC, or XL minus XC whole square. And let me remove all this so that we can just do a little bit of things here. So we have got one thing, what we wanted to do, what were our aims. Our aims were to find out, one among the aims were was to find out the magnitude of the current. See, we have got the magnitude of the current in the LCR circuit. What is that? That is V0 by square root of R square plus XL minus XC whole square. Okay, so this is actually, see this XL, this is actually omega into L, and XC, that is 1 over omega C. I can just put the value over there so that I get, this is Z, right? So Z will be actually square root of R square plus omega L minus 1 over omega C whole square. Okay, so this is the case. Okay, so we have got impedance, we have got expression for the current, magnitude of the current. Now, can we write the expression of the current? Answer is yes. We can be able to write. See, we can see here. See, from this phasor diagram, what we see? We see the current is actually ahead of the voltage by angle phi. So what we can write then? See, V is actually V0 sine omega t, right? Then can we write I is equal to I0 sine of omega t plus phi? This is the actual expression for the current, where V0 is, see, I0 is V0 by Z, or square root of R square plus omega L minus 1 over omega C whole square. Okay, that we can write. But what is phi? How to find out phi? See, phi, so from this figure I can find out the phi. So tan phi will be is equal to, tan phi will be is equal to perpendicular by base, and this is actually hypotenuse, this is base, this is perpendicular. So it is actually, if I write in terms of vector, so VC minus VL, this vector, divided by, I think I should not write in terms of vector, let me write in terms of, these are actually voltages. Okay, magnitude of the voltage I can just take. Okay, so V0 L or V0 C and V0 L. Okay, better to actually write, if I take the magnitude of this, magnitude can be reversed also, doesn't matter. Okay, let me just consider VL is greater than VC for the time being, so that we can write this as V0 L minus V0 C. Okay, at least we have to take the modulus of that, and divided by base is VI. Yeah, So this is the angle actually, tan phi. So B0 LC, this could be written again in terms of XL minus XC divided by R. Okay. Now see, we can just draw a plot, we can just draw a plot, like draw a figure between impedance, suppose this is impedance Z, so that is R square plus this. So phi should be between R and Z. So this is suppose R, and so this is Z and this is XL minus XC. Okay, and this is Z. Okay, and this is the angle phi. So what is this? Tan phi is equal to XL minus XC divided by Z. Okay, what is cos phi then? Cos phi will be is equal to, see, cos phi means excuse me, yeah, I'm sorry, there was a power cut due to uh, there is a rain actually at this place today in the evening, and thunderstorm as well. So there is a power cut, but anyway, I have got the connection of internet from my mobile hotspot, so we can continue the discussion. So what I was discussing is that, see, if I draw Rz and this xc minus xl. So phi is between r and z. So cos phi will be r by z. Okay, this is actually a useful term which we are actually going to use when we are solving problem. We will be using this, and while discussing power in AC circuit, we need this r by z. R by z is equal to cos phi. So if we draw this kind of diagram, okay, so we have see then so what is the summary of this phasor diagram method? So we have got the current. We see current is actually I0 sine omega t plus phi, where I0 is equal to V0 by square root of square root of r square plus xl minus xl whole square, or other way. So this is called impedance. And what we got is phi is tan phi is xl minus xc by z. Okay, now we'll just see whether the same result we get while doing analytical method. Okay, now we are going to do analytical method. So I can directly write, if this is v is equal to v0 sine omega t, I can directly write this as say v of r plus vl plus vc. I'm just taking the magnitude at the like directly, and this is v. Okay, so this I can write ir. This I can write if I take the instantaneous values, so ir, and this I can take L di dt, right? And this is q by c is equal to v0 sine omega t. Okay, now see, this is q, right? So this I is I current, we can just bring in terms of charges q. So r dq dt, say this is L d2q by dt square plus q by c is equal to v0 sine omega t. All right, now see, this is actually becoming a second order differential equation, and if you are familiar with post damped vibration, damped oscillation, post damped oscillation, this equation is actually exactly a post damped oscillation kind of equation, kind of post damped oscillation. Okay, post damped oscillation. All right, now we have to solve this equation to find out what is current. See, we will solve for q. We have to solve for q, then we will just take time derivative of q so that we get the current. I'm just thinking that how to solve this problem. See, always it is easier to solve this problem if we can guess the solution somehow. Okay, see, I can have a best guess as q is equal to q0 sine omega t plus theta. I can just guess this like this. Okay, let us say the solution for this equation, solution for this equation is this. I'm just supposing. Now what I'll do, I'll just take double derivative, first derivative, etc. So dq dt will give you q0 omega cos of omega t plus theta, right? What about second derivative? Second derivative d2q by dt2 or dt square. Okay, I can just, let me write like this. So see, if I just take the derivative of this part once again, what I'll get? Minus q0 omega square sine of omega t plus theta, right? This I can get. So this is dq by dt, this is d2q by dt square. If I put this in this equation, I'm just taking this, I'm just writing this equation here. L d2q by dt square plus r dq dt plus q by c is equal to v0 sine omega t. Okay, if I put this, see L into, we have got minus omega 0 square q0. Okay, look here, sine omega t plus theta. With single derivative, we know this is omega 0 q0 sine omega t, sorry, this will be cos omega t, cos omega t, cosine of omega t plus of theta. Q by c, I'll write q0 by c, then it will be sine omega t plus of theta is equal to this v0 sine omega t, the supply voltage, right? Now look, this thing we can actually make a nice form. Okay, we can actually divide all of them with omega 0 first, then we will get omega 0 L here with a minus sign anyway, q0 sine omega t plus of theta. Here I'll get q0 by omega 0 c. I don't know why I'm writing omega 0. There is no omega 0. I am just writing omega 0. Okay, by mistake. This is omega. That's just omega. Okay, so this is omega. Omega c sine of omega t plus theta, right? And see, with this, it is omega will be going off. This will be cos of, I think one r will be there. R will be there. Cos of omega t plus theta. excuse me, I'm back. Okay, so it is cos of omega t plus theta, and this is v0 sine omega t, again this side. Okay, I would have actually striked out this q0. Okay, q0, let me just strike out by dividing this by q0 here, so that I now see what I get. I get 1 over omega c minus omega L whole into sine of omega t plus theta. Okay, plus this is cos of omega t plus theta. Okay, so now, I think here on R I missed. Sorry, not here. Here I one R will be there. R, right? So I can further do one thing. This is V0 by Q0 sine omega t. So R by Z, I'm writing one thing. I'll just multiply. I'll be dividing with Z all the sides. Okay, both sides I'll be dividing with Z. So R by Z cos of omega t plus theta. This is 1 over omega c minus omega L, okay, by Z, and this is sine omega t plus of theta, right? And this side it is V0 by Q0 Z. I'm just dividing both sides sine omega t. Look now, I have to solve it in terms of either cos or sine. So I'll be using trigonometric identity just by taking this R by Z as cos phi and 1 over omega L minus, sorry, 1 over omega C minus omega L as suppose sine phi. This is sine phi. Okay, so look what I get if I put this R by Z as cos phi, cos of omega t minus, sorry, plus theta. Then we have got, sorry, 1 over omega c, that part I have written as sine, right? Sine phi and sine theta, sine omega t plus theta, sorry, is equal to V0 by Q0 Z sine of omega t. So look what we can write, this I can write. See, cos of A minus B will be cos A cos B plus sine A sine B, right? This is a trigonometric identity. So from here, using this, I can write this as cos of cosine of A minus B. Let us say this is A plus of theta minus b is phi is equal to sine. Okay, so this is v0 by q0 z. Somehow I think I have missed on omega somehow, omega c liquidity. Fine. All right, let me just see how we go. This is sine omega t, right? So if we compare this to what we are getting, just a minute. I see there will be omega 0 because omega here also because I'm dividing. Okay, there will be omega here also. In the right hand side also there will be omega. So here will be 1 omega. Okay, omega. So what we are saying here, see if we compare both sides, look I am writing here once again omega q0 cos of omega t plus of theta minus phi, and this is v0 by z, v0 by z sine omega t, this thing. Okay, all right, so if I compare this two, you look, if I compare this two I get v0 by z is equal to omega q0. So this has got, see this has got the dimension of current. I can write this as I0. So I0 is q omega 0. So we have got one thing, magnitude of the current. Now if we compare this sine and cosine, this term trigonometric functions, then you know we will get omega t plus theta minus phi. This is nothing but pi by 2. That means what? That means phi is equal to, or theta, I will write theta. What is theta is equal to? For theta is equal to omega t plus phi minus pi by 2. Okay. All right. So now see we had initially guessed the solution as q is equal to q0 sine of omega t plus theta. So here I can write this q is equal to q0 sine. See omega t theta, in place of theta I'll write this omega t plus theta. Uh, Omega t plus theta. Okay, so this will be minus, actually minus. Theta will be this, or omega t plus theta we can directly write omega t plus theta. Okay, so we can write this as I'm sorry, this I think just a minute. This is equal to, so this is equal to omega t plus, or sorry, omega t minus of pi by 2. This is that. right thing to do. Okay, this is the one. So theta will be is equal to minus pi by 2. Comparing these two, actually comparing plus pi. Okay, now theta, in place of theta we can put it, in place of theta we will put omega t plus pi minus pi by 2. So this will be actually cos of omega t plus pi. Then what will be the current? See, I'll just take dqdt. So I'll get I0 with a minus sign, I think cos of theta. Let me see. Yeah. In case of, yeah, so current you will write, yes, cos of theta. So current we had, okay, let me just go here. So what we had, current is equal to I0 cos of omega t plus theta, right? Let me just put the value of theta. Theta is actually uh, pi by 2 minus pi by 2 plus pi. Okay, this value only will put here. Okay, so I0 cos of omega t plus pi minus pi by 2. So this is actually I0 sine of omega t plus pi. See, this is actually dq dt. Okay, or I, instantaneous value of the current. Instantaneous value of the current, we have got I is equal to I0 sine of omega t plus pi. So the current is actually, current is I is ahead of V, applied V by pi phase. Okay, so this is what we had actually seen in case of phasor diagram method also, right? We had seen this same thing here also. Look here, see, the current is actually ahead of voltage, resultant voltage or the applied voltage by angle phi. So same thing we are getting by analytical method also. All right, so what is phi here? See, if you remember what was phi, see what is phi here. R by z we have taken phi. See, I'll just take it here. See, R by z, and see here also the z is actually taken as, z is, first of all, what is I0? I0 we have got omega 0 into q, sorry, omega q0, omega q0, omega q0. This is actually magnitude of the current, magnitude of the current. Okay, in the LCR series circuit. Oh, all right, so we have got this. Now what is this impedance? Impedance is actually Z, which is here also R square plus omega L minus 1 over omega C whole square. And phi is how much? Phi is actually, see, cos phi you have got sin phi. So sin phi by, so tan phi is equal to sin phi by cos phi, right? So sin phi you have taken how? How we have taken sin phi? Sin phi you have taken, see, we have taken 1 over omega c minus 1 over omega L, sorry, minus omega L, omega L. In fact, we can take the magnitude of this divided by Z, and this is R by Z. So Z going off, so it will be 1 over omega c minus omega L divided by R. Okay, so that means XC minus XL. So what is the thing we are getting here? Tan phi is equal to XC minus XL divided by R. Let me check whether we have XL minus XC. XL minus XC you have taken. Actually, we are taking the magnitude, so it doesn't matter what we are taking exactly. So it is actually, since we are taking the magnitude, doesn't matter here. Okay, but obviously, depending on the value, we have phase negative and positive. Let me just tell you one thing here. So if we just keep the uniformity of the definition of tan phi, okay, so we can write XL minus XC. If we can write this, see, when XL is greater than XC, then phi is positive actually. Okay, phi is positive. All right, so phi is positive. So in this case, it is called the LCR circuit. LCR circuit is LCR circuit is LCR circuit is predominantly inductive circuit. Inductive. Okay, and when XC is greater than XL, then phi is actually negative. That means LCR circuit is predominantly capacitive circuit. Okay, predominantly capacitive circuit. Okay, and see, one good thing I can just tell you, if XC and XL both are same, then it is actually purely resistive circuit. Purely resistive circuit. This I'll discuss in the next class, and also power in the AC circuit will discuss in the next class. Okay, so when XC is equal to XL, then phi is actually 0. When phi is 0, so then it is purely resistive circuit. That means current and voltage are in the same plane, and here the dissipation of the power will be maximum, and also the all the power will be dissipated through R, and the current in the circuit will be maximum. Okay, so this is the case. Okay, so we'll stop it here for today. In the next class, we'll be discussing resonance, then power in AC circuit. So resonance in LCR circuit and power in all the circuits, we will just see how the power is. Okay, and when we discuss resonance, we will be discussing sharpness of resonance, quality factor. These are important terms in resonance. And sharpness of resonance, then quality factor, all these things we will be discussing in the next class. Okay, all right, so thank you for your patience. Bye for today.